Hello everyone, my name is Neil Jackson and I'll be going over problem number 1, the cuckoo clock from test 3. So, the first thing that it asks us to find is the speed of the cuckoo right before it hits the fly. It's not a fly, it's actually a picture of Buzz. So that's a little criticism there. So, this is right before the collision and we have a spring, so we're going to use the energy principle to solve this. So, we know that the total change in energy is equal to work plus heat, which is 0 in this case. And we can rewrite this as the change in kinetic plus the change in spring potential is equal to 0. All right. Now we have a final and initial for each of these energies. So we can rewrite this as the final kinetic added to the final spring is equal to the initial kinetic plus the initial spring, okay? And then from here, it becomes pretty much simple algebra and some manipulation. We just plug in all of our known values. Half mv naught squared plus half k s naught squared. All right, and we have started with the energy principle, we've expanded it, and now simple algebra to find v sub 1. All right, so move everything but this term over to this side, multiply by 2, divide by m, take the square root. Easy stuff. And we wind up getting that the speed, or v sub 1, is equal to the square root of v naught squared plus spring constant over the mass times s naught squared minus s sub 1 squared. All right, there's part A. So part A is asking us for, it wants the maximum distance d that the cuckoo and the flyer travel before coming to rest, okay? So the cuckoo and the fly, cuckoo and Buzz are together in this, at the start of this problem. So we have to use the collision formula and the momentum principle to find that new speed once the two particles collide. And so we know that delta P, this is A, this is B, delta P is 0. So we know that the final momentum is equal to the initial momentum. Thereby we can say mv sub 1 is equal to the combined masses times this new velocity. And we're saying the combined masses because the Buzz and the cuckoo are sticking together, right? It's an inelastic, it's a maximally inelastic collision, all right? Solve for this new velocity, and we wind up getting that it is m over m plus m, big over big plus little, times v sub 1, all right? And then from this, with this new spring, we can now find the distance d which the spring moves, okay? So we can start off using the energy principle again, and we're gonna start off using this equation right here because it's the same setup, except we know that the final kinetic energy will be 0 because when Ke is equal to 0, the object is at rest. So we wind up getting the final spring potential energy is equal to this kinetic energy of the combined masses, because our initial is when the two particles first collide, half k sub s 1 squared. All right, and once again, huge algebra, find the final, stretch, and we wind up getting that is the root of big M squared over k, big M plus little m, times v sub 1 squared plus s sub 1 squared. All right, and then we can infer from that d is equal to s sub final minus s sub 1. There's part B. Part C asks us to find what is the change in internal energy of the stuck together cuckoo and Buzz in terms of distance, okay? So internal energy, we know we're gonna start off with the energy principle once again. So we know that delta E is equal to W plus Q, which is 0. And we know delta K is plus delta U sub spring plus the third type of energy, which is the change in internal energy. If I can spell internal, and that's going to be equal to 0. All right, so U sub spring, that's 0. There's nothing going on with the spring. Everything's stuck together, and it wants to know the internal energy. The spring is external, okay? So delta E sub int is equal to negative delta K. And we found that earlier, and so we can say that this is the negative of half m plus m over big M plus little m to be squared v sub 1 squared minus half mv sub 1 squared. And we wind up getting with this, just multiply everything out, multiply by -1, wind up getting that the change in internal energy is half little m times v sub 1 squared minus half m squared over big M plus little m v sub 1 squared. And that is how you do the cuckoo problem from test 3. Thank you.